Hello. Today we're going to talk about line integrals. And first we want to talk about what they actually are, but also maybe get a little reminder of what happened in Calculus 2. So let me get the right tool here. In Calc 2, when you were calculating integrals, you would have, maybe some curve in space. Let me draw a better curve. Something like that. And you would evaluate from some x value a to another x value b. And we could say that one of the things that you were calculating in Calculus 2 is the area under f of x on the interval a to b. And that is if this maroon curve here is f of x. Okay. Now, when we get to 16.2, what we're looking at is having an octant, right? We've got X, Y, and Z, and then this is going to be kind of weird. Maybe I'll use my highlighters. So we've got some surface here. We can call that surface f of x, y. And then on the 2D plane, the xy plane, we have maybe some curve, C. And what we do here, so this is on the xy plane, and what we do here is we integrate f over the curve C. And so that's actually quite similar to what we were doing in Calculus 2, except now we have this three-dimensional surface. We're just going to fix that surface so that it's only over the curve, not over all xy values, but only the xy values that are on that curve C. I can show you a little picture. There's this picture down here on the bottom, but honestly, it's actually on the third page or fourth page. Okay, fifth page. Here we go. No, it's the sixth page. Wow, it's way out there. Okay, so I've got right here, I've got a curve C in the left picture, and that's the pink line that is on the XY plane. And if we can imagine like a curtain that goes straight up vertically from that curve, and then it meets up with the surface in another curve. So this is like where C, um, so vertical plane through C, our curve that meets the surface. And then over here in the picture on the right, now I've got the surface on there, and I can kind of highlight the curve C where it meets up with the surface. So we're not calculating volume anymore. We are actually looking at calculating an area, and it's the area of one side of that vertical plane, or not really a plane, vertical cylinder, right? Because it's parallel to one of the axes. So the vertical space that rises from the XY plane and follows along the C curve and meets up with the surface, we're going to be calculating the area of one side of that. And we'll talk more about that. I just want to kind of give you a visual right here. So I'm going to scroll back. I hope this doesn't make you dizzy. Going back this fast, and we're back in the beginning. Okay, so we're going to calculate line integrals in the plane or in space. That means we could deal with 2D or 3D. And we are going to have to assume that our curve C is a smooth curve in 2D, and it's given by parameters. And in particular, it has parameters x of t and y of t, which means that we are finding a vector function of that curve. In other words, what we're doing is we're going to parametrize xy to t. So to say that, we're going to integrate in terms of one variable. So this is a single integral. So we need to parametrize xy to just one variable t. Okay, we've been doing this. We started this in chapter 13. So this part is not new, but that doesn't mean it's easy, right? It's hard to give the motivation back in chapter 13 about how important it will be later on in chapter 16, but now I can say it. What we learn in chapter 13 is so important for what we need to do here in chapter 16. So we've got now a parametric function. That's what we call r of t. It has components x of t and y of t. We could even go up one more dimension and have a z of t. And t is going to run between two numbers, a and b. And sometimes we'll be given those, and sometimes we'll have to figure those out. So we're going to divide our parameter interval, AB, into subintervals. And so this is kind of like the Riemann sums part of this. I've got this picture on the left here. And the idea is, we start at A, we go to B, but along the way, we break up that interval into tiny little pieces, like t sub I minus 1 to t sub I. And then those t values are going to correspond with some point on the curve C. And then we can create like a little subarc on that line. And each subarc will have a length of delta S. Okay, so we could call that some delta S. So for any point, and we'll call those x star, y star, any point on that little subarc, we can find the function value, the surface value at that point and multiply it by the subarc length. And then we would add all those up, and then we would take the limit as those little subarcs get smaller and smaller. And what we get is this integral right here, the integral over c of f of xy ds. And what this is it's the area under f of xy along the curve C. Okay, now ds, let's see what that is. So this integral that I've written here, this is a line integral, and the differential ds is just the arc length, right? So we're going to take a height and we're going to multiply it by a length, and that's going to give us an area. Now, we learned in chapter 13 a way to calculate arc length. It was also covered in Calc 2 as well, but probably much more readily available in your memory from Calc 3 in chapter 13. So arc length, we learned, was this integral right here. So we denote it as L, and L is equal to the integral from A to B of the magnitude of the derivative of our vector function times dt. So we will be either given a vector equation or we will have to create one. Once we have it, though, we will need to calculate r prime and then take the magnitude of that. Now, if you remember, if we take the magnitude of r prime of t, what that gives us is a square root of the sum of squares of the components. The components will be derivatives. They'll be the dx dt and dy dt, and we could up that one dimension and go to dz dt as well. And so we're going to find r prime of t. We're going to take all the components, square them, add them, and stick them underneath the square root. That is our differential, okay? And so we kind of have to remember that. I've given us a whole slew of formulas right here. They all are saying the same thing, but they all have slightly different notation in the hopes that you remember at least, maybe two of them. Now, the first one gives us the least amount of information. Like if I saw this, the integral over c of f of xy ds, it's not entirely clear what the parts are, okay? But if I see this one right here, f of r of t times the magnitude of r prime of t, that's a lot more clear. that's telling me I need to take my scalar function f of xy, and I need to replace all x's with whatever the x component of r of t is, and I need to replace all y's with whatever the y component of r of t is. And then I need to multiply that by the magnitude of r prime of t. So this is more clear. And then this last representation explicitly states all the parts. It's telling me, instead of looking at f of xy, look at f of x of t, y of t. That's making this like the most clear. And then I've got an explicit formula for the magnitude of r prime of t in there. So just know that these all mean the same thing. Check out your formula sheet, see which one I gave you on the formula sheet, and see what you're going to be responsible for knowing from that formula sheet. Okay. In the next line, I've just upped the dimensions. So the only difference in this next line is that now we have three-dimensional f of x, y, z. And so that means r of t will have a third component, the z of t. And r prime of t will also have a third component. It'll be the dz dt. Okay. So in each one of these, you need to remember that we're using this guy, ds is equal to the magnitude of r prime of t dt. Okay. Now, the value of the line integral does not depend on the parametrization of the curve if the curve is traversed just once as t increases from a to b. Okay. If it turns out the parametrization does not fully cover the curve, then it's not a good parametrization. Or if the parametrization ends up taking you along your curve twice, then you're getting too much, right? So whatever your parametrization is, you need to make sure that it fully covers the curve in question. If our function f of xy is a positive function, then the line integral represents the area of one side of the curtain with base c, whose height is above each point xy, is this f of xy. So in other words, just one side here. I wouldn't get the other side. It would only be one side, one or the other. So I like to think of it as like if you had a fence, you were painting it, you would want to paint both sides, but that would be like the double of the area, right? You'd have to double the amount of paint you would need for two after you've done one. So what we're doing is we're figuring out how much paint you would need on one side of the fence in order to do the job you want to do. The other thing for you to make note of is that if f of x, y, z is just 1, then what happens is up here, our line integral over c of f of x, y, z ds would just equal the integral from a to b of 1 times the x prime of t squared plus the y prime of t squared dt, which would just equal arc length. Okay, so that's in only the case where f is equal to 1. So we've seen that before. We saw that with a double integral. If the integrand is just 1, then a double integral can be calculating area. And we also saw with a triple integral, if the integrand is just 1, then we're also calculating volume. So we just want to always tie together like how these things are related to each other. So arc length and line integrals are extremely related because arc length is the differential of a line integral. All right, so let's try some examples to see like how this all works. Here we're asked to evaluate the line integral over the given curve C, and we have the line integral over C of y ds. And one of the things I like to remind myself anytime I'm working through a line integral, I remind myself that the line integral over C of f ds, or f of x, y ds, is equal to the line integral of f of x of t, y of t, times the square root of x prime squared plus y prime squared dt. I just write that down for myself, and we go from A to B. The more I write that down, the more likely I am to remember it and to remember how to use it, because sometimes it's easy to look at a formula sheet, and if you actually haven't taken the time to get to know the different integrals that we're working with, the formula sheet won't even be helpful. So get to know it, write down your formulas, know them. All right, so based on this, I need an x of t and a y of t. I need an x prime of t and a y prime of t. Just remember also that r is equal to the vector with components x of t, y of t, and r prime is equal to the vector with components x prime of t, y prime of t. So when we see notation like this, where c is defined by x equals t squared, y equals 2t, and t goes from 0 to 3, they've just given us the parametric form of a vector function. So I could easily take this and say, oh, well, r of t is just equal to a vector with components t squared and 2t. And so r prime of t is just equal to a vector with components 2t and 2. Okay? That 2t is not very clear. All right. And so I've got my pieces. I know that x of t is t squared. I know y is 2t. I know x prime is 2t. And I know that y prime is 2. So I can plug all this stuff in. I'm going to go ahead and do that. This integral is equal to the line integral from 0 to 3, because those are the bounds they gave me for t. The y is my f of x y function. It's just equal to y. So there's a y in there. I need to replace it with 2t. So I do that. ds, remember ds is equal to the magnitude of r prime of t dt, which is also equal to the square root of the sum of squares of the derivatives from r prime of t. Okay, so I'm going to pop those in there. Got my square root. X prime is 2t, and then I square it. Y prime is 2, and then I square it, and then I have a dt. All right, let's clean this up a little bit. This is equal to the integral from 0 to 3 of 2t times the square root of 4t squared plus 4 dt. There's a 4 in common with each of those terms. I can take out a 4 and square root it. It'll be 2. It's going to join the 2t on the outside and become 4t, and leave behind just a t squared plus 1 dt. This is a u sub. So I'm going to do a u sub off to the side here. In my u sub, I let u equal t squared plus 1, and then du is going to equal 2t dt. In my integral, I have 4t, so I'm going to look at multiplying everything by 2, so that I have 2 du will replace 4t dt. And now I have full replacements for everything. Okay, so I can go ahead and set up an indefinite integral of, looks like I just have a 2 and a u to the 1/2 power du. U to the 1/2, when I integrate that, it's going to be u to the 3/2 divided by 3/2. So it'll be 2 times 2/3 u to the 3/2, which is 4/3 u to the 3/2. Okay, going back to my integral. I can integrate. I've got 4/3. U is t squared plus 1 raised to the 3/2 power. This will get evaluated from 0 to 3. All right, I'm going to pull the 4/3 out and handle the other stuff. So I'm going to plug in 3. 3 squared is 9 plus 1. I get 10 to the 3/2 minus the evaluation at 0 just leaves me 0 plus 1, so I get 1 to the 3/2. I can rewrite this one more time. This is equal to 4/3 times 10 square root 10 minus 1. And that's our final answer. This is the value of the area of one side of the curtain that's formed when we look at the intersection of our curve coming up and meeting with our surface. Okay. Next problem, we're going to evaluate a line integral of 2x ds, where c consists of the arc C1 of the parabola y equals x squared from 0, 0 to 1, 1, followed by the vertical line segment C2 from 1, 1 to 1, 2. I need to draw this. So I've got my xy axes. It looked like everything was in the first quadrant. Y equals x squared from 0, 0 to 1, 1 is parabolic. So I've got this shape. That is C1. And then they tell me that there's a C2 part of this, and it goes from 1, 1 to 2, 2, and is just a vertical line. So this is C2. What they're telling me is that my curve is 2 pieces. And so I have to deal with this in 2 pieces. I'm going to look at C1 first. C1 is where our function is y equals x squared. I need to get a parametric functions for this. If I let x equal t, then y equals t squared. That would work. I do this sort of thing anytime I have an explicit function, like y equals something in terms of only x. Then I just go ahead and let the independent variable be t, and then the dependent variable will be a function of t. So then my r of t is equal to a vector with components t and t squared. It looks like x and t are the same, and so looking at my points for x goes from 0 to 1, so I can say that t goes from 0 to 1 as well. Now I need r prime of t. R prime of t is 1 and 2t, and then I need the magnitude of our r prime of t dt, because that's going to give me my ds. So I'm just trying to get all my parts. This is going to give me the square root of 1 plus 4t squared dt. Okay, so those are all the parts for C1. I also need all the parts for C2. C2 is a vertical line segment, and that vertical line segment is run, if I was to draw it fully, down, it would go through, it would go through my x-axis, which I have improperly labeled. I have no idea why. I'll blame the coffee I've been drinking. All right, so C2 can be modeled by the equation x equals 1. Okay. Now, as we travel along C2, we start at y equals 1, and then we go up, 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 and the y values are changing. It's just x is staying 1. So that means that we could let y equal t, and x is still going to be 1. No matter what t value y takes on, x is still 1. So then we can say that r of t is a vector with components 1t, and it looks like since y is going to equal t and y goes from 1 to 2, that means t goes from 1 to 2. Okay, then we find r prime of t, which will be 0 and 1, and then we find ds. ds will be the magnitude of r prime of t dt, which that gives me the square root of 0 plus 1 dt, which is just equal to dt. Okay, now let's see what this all means when we put it together. We are supposed to calculate a line integral over c of 2x ds, but c consists of 2 arcs, c1 and c2. That means we have to integrate over c1, 2x ds, and then add an integral over c2 of 2x ds. And that means I need to take the parts from c1 and put them in the first integral, take the parts of c2 and put them in the second integral. Okay, so I'll do the color thing as well to make this just a little bit more clear as to what gets what. So for the c1 integral, the bounds are 0 to 1. 2x, well, I go to my r of t, x is t, so I have 2t, and then I need my ds. ds we found to be the square root of 1 plus 4t squared dt. So that takes care of the C1 integral, plus the C2 integral. So I go to my C2 setup. It looks like t is going from 1 to 2. And then the 2x, well, in this one on C2, x is 1. So I have 2 times 1. And ds is just the square root of 1 dt. Okay. Now, in the first one, I have a u sub. So I'm going to go off to the side. I'll actually go over here and do my u sub. U will be the stuff under the radical, so it's 1 plus 4t squared. Du is 8t dt. I don't have an 8t, I have a 2t, so I'm going to divide both sides by 4. 1/4 du is equal to 2t dt. So now I have perfect replacements from my integral. So now it looks like I'm integrating 1/4 u to the 1/2 du. This becomes 1/4 times 2/3 u to the 3/2, which simplifies again to give me 1/6 u to the 3/2. Okay. The second integral is just 2 times 1 times 1, so it's just 2. Okay, so that one's not bad, but the first integral was a little bad. All right, so what we get is an integrand or an antiderivative of 1/6 1 plus 4t squared raised to the 3/2 power, evaluated from 0 to 1, plus 2t, evaluated from 1 to 2. With the first one, I will pull out the 1/6. I'll evaluate at 1. I get 1 plus 4, which is 5 to the 3/2, minus, evaluating at 0, I get 1 plus 0, so I just have 1 to the 3/2. And then for the second one, I get plus 2 times 2 minus 2 times 1. Okay, putting this all together, this gives me 1/6 times 5 square root 5 minus 1 plus 2 minus 2 gives me just plus 2 for a final answer. This is fine as an answer. I mean, technically we could distribute the 1/6 through and then we could combine things. So if you do go that far, it'll be, let's see, if we distribute, we have 5 square root 5 over 6 minus 1/6 plus 2, which I'll rewrite as 12 over 6. So this becomes 5 square root 5 over 6 plus 11 over 6. And then we could factor out the 1/6 again and leave behind 5 square root 5 plus 11. That would also be an acceptable answer for this problem. Okay, so this is how we handle when our arc C consists of 2 pieces. We just have to deal with 2 line integrals. The pain is that we end up having to parametrize twice, right? So you can imagine, like, the more pieces, the harder this gets. All right, third one, we want to evaluate the line integral over C of y sine of z ds, where C is the circular helix given by the equations x equals cosine of t, y equals sine of t, and z equals t. And t is going from 0 to 2 pi. So I'm going to kind of put this together in terms of vector functions. So I've got my r of t. They give us the components. They're cosine of t, sine of t, and t. I also want to lay out that f of x, y, z is equal to y sine of z, and f of x of t, y of t, z of t is different, because what we do now is we replace all x's with cosine of t, all y's with sine of t, and all z's with t. So I'm going to do that. I'm going to replace the y with, from the parametric function r of t, the y component is sine, so I have sine of t. And then z I replace with t, so I get another sine of t, for a grand total of sine squared of t. Now, in anticipation of having to integrate that, I need to rewrite that sine squared because we can't integrate a power of a trig function by itself, not a square. We need to use a power reducing formula. And that is going to be 1/2 minus 1/2 cosine of 2t. Okay, so I've taken care of my, my integrand from my line integral, but now I need to take care of the differential. So I need r prime of t, and that will equal negative sine of t, cosine of t, and 1. And then I need the ds. ds, remember, is going to be the magnitude of r prime of t dt. So that's going to be the square root of the sum of squares. So I get sine squared of t plus cosine squared of t plus 1 dt. Well, sine squared plus cosine squared is 1, and 1 plus 1 is 2. So this is just the square root of 2 dt. Okay, I think we're ready. I think we can put this in. So let's go to we have our line integral. Change colors here. We have our line integral over c of y sine of z ds is equal to the integral. They tell us the bounds are 0 to 2 pi. I found that y sine of z is sine squared of t, which we can rewrite as 1/2 minus 1/2 cosine of 2t. And then not a dt yet. Now ds we found to be the square root of 2 times dt. Okay, we're just about there. I can factor out a square root of 2 over 2 on this integral. Leave behind 1 minus cosine of 2t dt. All right, so the square root of 2 over 2 stays outside. Integrating, I get t, and then I get minus 1/2 sine of 2t, and this is all going from 0 to 2 pi. All right, plugging everything in, I have the square root of 2 over 2. Evaluating at 2 pi, I get 2 pi minus, well, sine of 2 pi is 0. And then evaluating at 0, I get 0 minus, well, sine of 0 is also 0. So I didn't get a whole lot of contribution there. My final answer is just going to be the square root of 2 times pi. And that's it. So that was looking at a three-dimensional case where f of x, or our scalar function is f of x, y, z, and now we have a three-component parametrization. And in this one, they gave it to us. We didn't have to come up with it, which is nice. So I want to stop right now. I'm going to make this whole section be 3 videos just because there's a lot to take in. So if you have any questions on line integrals of scalar functions, please reach out.